Hey guys, tonight we drift into one of the strangest chapters of the cosmos, where time feels like it might be lying to us. You're weightless as always, but something about the void tonight feels less like a lullaby and more like a riddle. All around you, the universe stretches not just in space but in story. Stars blink in the distance, each one sending out light that's traveled for billions of years, messages in bottles tossed from long-dead shores. You float just beyond the veil of the observable, where James Webb's golden eye peers back into the youth of everything. Except something doesn't quite fit. There are galaxies here. Bright, spinning, massive galaxies. Galaxies that shouldn't be here yet. It's like walking into a nursery and finding a fully grown adult reading the newspaper. You blink, check the timestamp, reread the data. Yep, that galaxy over there born just a few 100 million years after the Big Bang. It shouldn't have had time to form. And yet here it is, strutting through the early universe like it owns the place. You probably won't survive this. The sheer scale alone will squash your atoms, flatter than a cosmic pancake. But don't worry, you're not really here. You're more like a dream riding on photons. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know in the comments where you're listening from and what time it is there. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You drift closer. The galaxy in front of you is labeled Sears 93316. Not that labels matter much when you're hovering in vacuum, but it helps scientists keep track of the surprises. This one, it's been nicknamed the Rule Breaker. Its light has been traveling for over 13 billion years, but it already shows signs of maturity. Complex structures, star formation, maybe even a developing spiral. It's like finding architecture in a place that should still be mud huts and hopeful campfires. When James Webb Space Telescope first spotted galaxies like this, scientists didn't panic. Not at first. They squinted, ran the numbers, muttered things like preliminary findings and possible redshift errors. Because surely these couldn't be real. Not this early. Not this developed. The universe was only a few 100 million years old at that point. In cosmological terms, that's baby's first breath. But then, they kept showing up, one after another, farther and brighter and older than expected. The standard model of cosmology, the LCDM model, predicts a slow, patient unfolding. First, the Big Bang. Then, after a few 100,000 years, the formation of neutral atoms. Then, the cosmic dark ages. Then, light begins to return. Stars ignite, galaxies slowly form like swirls in cooling soup. Except, soup doesn't usually form skyscrapers. And that's what some of these galaxies look like, cosmic skyscrapers built overnight. The math struggles. You float through the equations in scientists' minds, where mass star formation, rate dust content, and halo growth dance around each other like tired ballroom partners. But nothing explains how these galaxies had enough time to form at such scale. Not without rewriting the tempo of the whole dance. There's a familiar metaphor among astrophysicists. The early universe was like a toddler playing with building blocks. Basic shapes, limited reach, lots of stumbling. But these galaxies aren't toddler-built. They're adult-level engineering. Some even host what might be supermassive black holes. At 400 million years old, that's like finding a mortgage broker inside an egg. And that brings the first gentle tug of worry. Because either something about how we read light is wrong, or something about how the universe behaves is incomplete. Maybe both. You coast backwards, slightly drifting between two ancient galaxies. Their light crackles around you like whispering thunder. Your presence doesn't disturb them. You're a ghost among ghosts watching a crime scene billions of years cold. Here's a thought: maybe time as we understand it isn't linear. Maybe it folds, swirls, dances like gravity does. Some fringe cosmologists have quietly entertained this for years. What if the fabric of space-time is more like a crumpled blanket than a clean sheet? But let's not get ahead of ourselves. Right now, let's stay in this moment where you float between impossibly old galaxies in an impossibly young universe. One of them flickers. Not visibly, not like a dying star, but in data, its spectral fingerprint has the hallmark of early oxygen. That's the cosmic equivalent of a child scribbling poetry in a language it shouldn't yet know. You peer closer. The light from this galaxy has been stretched redshifted as the universe expands. That redshift, normally a precise ruler for estimating age and distance, seems to mock you now. Because according to it, these galaxies are at a redshift of Z12 or higher. Translation: you're seeing them as they were when the universe was just 300–400 million years old. And yet they're bustling. Now a voice in your head, borrowed from Earth's ivory towers, speaks softly. Maybe star formation began earlier than we thought. Sure, maybe. Or maybe the Big Bang timeline needs more than a nudge. It's worth noting science doesn't mind being surprised. It lives for it. But it does get grumpy when reality refuses to fit the model. This is one of those moments. You glide a bit farther, watching a cosmic nursery swirl with purpose. Stars burn blue and white, young, massive, hot. Dust clouds swirl like the breath of sleeping giants. Gas collapses into filaments and sparks and gravity wells. It's beautiful and weird and possibly wrong. One researcher back on Earth described the sensation as like being told gravity is optional. She wasn't exaggerating. If these galaxies truly exist this early, it could mean our models of structure formation, how matter clumps and builds over time, need to be reimagined. That's not just rewriting a chapter. That's ripping out the whole table of contents. And yet, you're not panicking. Because in the silence of space, everything feels calm, even contradiction. You float there, watching the early universe hustle like it's late to its own birthday. Stars flicker in and out of life. Galaxies spiral and merge and blaze like divine pinwheels. And somewhere in the cold vacuum, a telescope the size of a tennis court quietly feeds data back to Earth, where the real confusion has only just begun. You drift backward in time. Well, not really backward, because time in space doesn't tick like a wristwatch. It pulses, stretches, curls inward when no one's looking. But you feel like you're gliding into younger and younger moments of the cosmos. Except, the cosmos doesn't behave as expected. Tonight, you're sifting through the universe's baby photos. Or rather the cosmic equivalent of an infant's scribbles, only to find full-fledged sonnets. Thanks to the James Webb Space Telescope, humanity now has access to the deepest snapshots of the early universe ever taken. Its infrared vision, sharper than anything that's come before, lets it see through cosmic dust and catch light that's been traveling for over 13 billion years. It's like getting a postcard from the dawn of time written in redshift, so you hover there right at the edge of what's observable. This is the realm of Z10, not a place, but a time, when the universe was less than 500 million years old. Back then, stars were still figuring out how to burn, and space was mostly dark and cold, like the pause before a candle is lit. And yet, there are galaxies here, dozens, maybe hundreds. Webb sees them with eerie clarity. You drift by one, a compact little overachiever, its starlight smooth and reddish, telling you it's traveled a very, very long way. It's one of many in the JWST early release science images. The data came fast and messy, at first galaxies far brighter and more massive than any model said was possible. It's like someone turned on the universe too early, and nobody remembered to tell the physicists. A whisper from Earth echoes in your thoughts. These galaxies are too evolved, too luminous, too structured for their age. The words come from researchers sitting in stunned silence, staring at screens full of data that shouldn't exist. You can almost imagine the headlines. Webb Telescope finds galaxies that break the universe. Early cosmos more crowded than expected, scientists baffled by ancient light. You chuckle. If the cosmos had a baby book, this section would be full of scribbled question marks and coffee stains. But let's pause for a moment and talk about the baby pictures themselves. The cosmic microwave background CMB is the universe's first known snapshot. It dates back to about 380,000 years after the Big Bang. Back then, the universe had cooled just enough for atoms to form. Light could finally travel freely. That light, now stretched into microwaves by the expansion of space, is what we detect as the CMB. It's a fuzzy, warm blanket draped across the sky, a murmur from a time before stars. And what comes next? The Dark Ages. A few 100 million years of darkness and invisibility. No stars, no galaxies, just slowly forming clouds of hydrogen building pressure and density, like a held breath. Then eventually, Ryanization. That's the moment stars ignite, and ultraviolet light begins to tear electrons off atoms again. The fog lifts, the universe becomes transparent. The first galaxies sparkle to life. That's where you are now, on the very edge of that transformation. And yet as you float here, you notice something odd. The galaxies you're seeing aren't tentative, shapeless fuzzballs. They're structured. They're bright. Some seem to be forming stars at a furious pace, hundreds of solar masses per year. That's like building an entire sun every few days. One glows with a radiance so intense you'd assume it was much younger, except it's one of the oldest visible objects in the sky. Its redshift puts it right in the middle of Ryanization, but it looks like it's been partying for 1 billion years. You drift closer. A faint trace of oxygen appears in the spectral data, an element forged in stars and spread by supernovae. That means this galaxy isn't just forming stars. It's already cycled through at least one generation of them. You're not looking at a first draft. You're looking at a second edition, which begs the question, how did it have time for that astrophysicists meanwhile shuffle their timelines around like puzzle pieces that don't quite fit? Maybe galaxy formation started earlier. Maybe there were more dense regions than expected. Maybe these galaxies formed in pockets of hyper-efficiency, like overachievers in a cosmic classroom. But none of that fully explains what we're seeing. There's a soft grumble in the back of your mind, an old lingering debate. Are we misunderstanding what redshift means at extreme scales? If redshift isn't just from cosmic expansion, but also influenced by unknown local effects, then maybe these galaxies aren't as far or as ancient as we think. But then again, redshift is our best cosmic ruler. Take it away, and the entire model starts to sway like a house without its foundation. Some fringe thinkers whisper about tired light theories, an old idea that light might lose energy over distance for reasons unrelated to space expanding. But that theory was mostly shelved decades ago, like a dusty tome full of typos. Still, when faced with anomalies, the mind wanders. You hover near another galaxy, this one even brighter. There's speculation. It could be lensed a distant galaxy, magnified by a nearer one bending its light. That could make it appear brighter and closer than it really is. Gravitational lensing has explained other cosmic mirages before. But here's the catch. Not all of them are lensed. Not even most. That excuse only works a few times before it sounds like cosmic gaslighting. So now scientists must choose between uncomfortable options. The galaxies are real, and the models are incomplete. The galaxies aren't what they seem, and our tools are flawed. Or something even weirder is happening. And honestly, the last one is starting to sound the least weird. Still, science doesn't throw out theories at the first sign of trouble. It pokes prods and waits. Maybe the sample is skewed. Maybe the mass estimates are off. Maybe JWST's instruments are picking up light from overlapping sources. But deep down, you know it's more than that. Because you're here. You're drifting between galaxies that shouldn't exist. You're watching them shine with the kind of defiant glow that suggests nature didn't read the rulebook or read it and laughed. One last flicker catches your eye. A cluster of galaxies not isolated, but already interacting. Their mutual gravity has pulled them into a gentle swirl, like dancers gathering at a cosmic ball. But there's something off about the tempo. They're moving like seasoned performers, not clumsy first-timers. You linger on the edge of their spiral, listening to the silence of space, filled now with one undeniable truth. The universe's baby pictures are wrong. And they're not shy about it. You drift onward deeper into the ancient glow like a dust mote caught in the breath of eternity. The darkness here isn't empty, it's thick, velvety, filled with the quiet humming tension of unsolved equations. Behind you, trail the afterimages of galaxies that defy their birth dates. Ahead, the silence sharpens. You're moving toward a problem, not away from it. You pass another galaxy no name, just a number, and a redshift so high it practically screams. This one's compact, but massive, already churning out stars at a rate that makes even the Milky Way look like it's dragging its feet. And here's the kicker, it's not alone. James Webb hasn't just found one or two precocious galaxies, it's found a crowd. An early cosmic cityscape dense with light and mass all jammed into a tiny fraction of the universe's infancy. It's as if the universe skipped adolescence and jumped straight to adulthood. Back on Earth, astrophysicists pace around whiteboards trying to fit this wild batch of observations into the neat framework of LCDM, the standard model of cosmology. That model, our most trusted map of the cosmos, says that galaxies grow slowly. They start as small clumps of matter merging over time to become larger structures. But these aren't seedlings. These are redwoods. Now comes the delicate part. You float along threads of theory, each more speculative than the last. One in particular gleams with odd promise-modified dark matter models. You've probably heard of dark matter. It's the invisible scaffolding that keeps galaxies from flying apart. Scientists don't know what it is, but they do know it's necessary. Without it, galaxies would unravel like a sock in a blender. The standard model assumes cold, dark matter, slow-moving particles that clump together, allowing regular matter to collect and form stars and galaxies. But what if dark matter isn't cold? What if it's warm or worse, fuzzy? In one variation called fuzzy dark matter, the particles are so lightweight, so ghost-like, that their quantum nature stretches across entire galaxies, like a cosmic jelly. This could suppress small-scale structures, but in the right conditions, it might actually accelerate the formation of massive ones. Emphasis on might. You glide through a simulation, a frozen mathematical dream. In one corner, standard dark matter. Galaxies form gradually. In the other, fuzzy dark matter. Galaxies form early but weirdly, clumpy, bright, short-lived, like cosmic firecrackers. The models diverge quickly, and neither fully explains what Webb is seeing. Another idea drifts into view: enhanced primordial density fluctuations. Basically, maybe the early universe had more extreme hot and cold spots than we thought. Areas of higher density, where matter clumped faster, forming stars and galaxies earlier. That might explain these early giants. But again, that's a patch, not a fix. The models allow for some overachievers, but not this many and not this luminous. And then there's the fringe, the wild edges of theory, where things get properly weird. What if time itself isn't behaving the way we assume? You chuckle softly in the void. That's not science fiction. Some physicists have proposed models where time isn't a fundamental dimension, but an emergent one like temperature. It appears when enough particles interact in complex ways. In such a view, early time conditions might play by different rules entirely. One lesser-known theory even suggests that the speed of light might have been higher in the early universe. Faster light means a different redshift behavior. Galaxies might appear older or farther than they really are. It's called VSL, variable speed of light. Radical sure. But it hasn't been entirely ruled out. Nothing gets thrown away in cosmology. It just gets shelved behind better evidence. Of course, each of these theories has its critics. Modified dark matter, too many free parameters, variable light speed, not enough testable predictions. Enhanced density fluctuations still doesn't match Webb's numbers. And meanwhile, the galaxies just sit there. Glowing, ancient, smug. You circle one of them slowly. It's about the size of the Large Magellanic Cloud, a satellite galaxy of the Milky Way. But it's far brighter, more tightly packed. Its light has been traveling for 13.3 billion years, and yet here it is, fully dressed, already dancing. What's stranger, some of these galaxies are dusty. Dust is made of heavy elements: carbon, silicon, oxygen, stuff forged in stars and spread by supernovae. Dust implies multiple generations of stars have already lived and died. But for that to happen in just a few 100 million years, it's like baking a 7-layer cake while the oven is still preheating. This shouldn't be possible. And yet, it is. One voice from Earth, calm and tired, offers a possibility. Maybe we misunderstood the early star formation process. Maybe stars formed faster than expected. Maybe the early universe wasn't quiet and slow, but chaotic and wildly efficient. A cosmic bootstrap operation, clumps of gas igniting almost instantly, feeding black holes, triggering more star formation, and spreading metals through space like butter on toast. But that still doesn't explain everything. Not the mass, not the structure, not the speed. You peer back toward the universe's early moments. The Big Bang, 13.8 billion years ago, isn't a point in space, it's a point in every space. Everything expanded from everything else. There was no outside of it, no edge. Just energy condensing, cooling, transforming. Now you wonder what if we've got that wrong too? Some fringe thinkers suggest the Big Bang wasn't a beginning, but a transition. Maybe from a previous universe or a cyclic one. In such a model like the ekpyrotic or conformal cyclic cosmology, theories our universe could have inherited structure from before time, like a genetic memory. Sound wild, Roger Penrose. Nobel laureate takes it seriously, and here among these ancient galaxies, it doesn't sound that wild. If anything, it feels oddly comforting. Maybe these galaxies are fingerprints from a cosmos that never truly began, just restarted. You watch one more star flicker into existence as though it's winking at you, or maybe mocking you. Because every time we think we understand how the universe grows, it hands us something bright and old and confusing. And then it gets quiet again. You linger in that quiet floating near the glowing bones of impossibly old galaxies, feeling like a guest who's shown up too early to a party only to find the music already playing, drinks poured, and everyone in mid-conversation. The vibe unsettling. The universe isn't waiting for you to catch up. It never was. Your gaze drifts toward the implications of all this. If galaxies formed faster than expected, if stars blazed and died before physics even got a foothold, what does that say about the timeline of everything? You watch the ticking of cosmic time, slow and syrupy out here. Our models have long told us that structure in the universe forms patiently, one step at a time. Dust into clouds, clouds into stars, stars into galaxies, galaxies into clusters like bricks, laid carefully by gravity's invisible hand. But these galaxies, these bright, massive things in the cosmic dawn, they feel like shortcuts, like someone fast-forwarded through the middle chapters of the universe's autobiography. And now you notice something even stranger. Some of these galaxies, these overachievers of the early universe, have already stopped forming stars. You're not sure at first, maybe it's a trick of the light, a calibration glitch in your imaginary instruments. But no, the colors are clear, the signatures are there. These galaxies are quiescent, not just old-looking, but genuinely winding down, already retired. Imagine a firework that explodes before you even light the fuse, then calmly turns to ash, while you're still blinking from the flash. That's what this feels like. You float beside one, now watching its quiet red glow. Not the bright blue of active star birth, but the deep ember-like tone of an aging stellar population. The core is cool, the gas is still. There's a kind of melancholy there, a hush like a library, where no new books will ever be written. Somehow, within just a few 100 million years, this galaxy burned through its raw material, formed generations of stars, and then stopped. You wonder what kind of firestorm must have roared through it to cause that. Maybe it was too efficient. Maybe it formed stars so fast and furiously that it exhausted itself in the blink of a cosmic eye. That kind of early burnout, though, would require extreme conditions. Conditions that push the limits of what we think galaxies can even do. And here's where things get a little hotter, a little more dangerous. Because nestled in the hearts of some of these early galaxies, yes, even now, are signs of something even more dramatic. You feel it before you see it, a flicker, a tug, a kind of gravitational growl in the background. Black holes. Not just any black holes, but supermassive ones. Already grown fat on starlight and matter already affecting their environments. Their gravitational pull reshapes entire galaxies like invisible engines sealed in silence. And yet somehow, they're already here. One of them sits just ahead of you. You can't see it directly, of course, it's the nature of black holes to remain hidden. But the light around it flares and twists, and the movement of gas is unmistakable. It's feeding, even now pulling matter inward, spinning up the surrounding disk into a luminous storm. This is a galaxy that, instead of gently building stars over time, has opted for a different script, one with jets, radiation and shockwaves. When black holes feed like this, they don't do it quietly. The energy they unleash can blow gas right out of a galaxy, cut off future star formation, and effectively kill the host before it gets a chance to grow old. It's a cosmic version of burnout culture, maximum output, minimal longevity. But here's where your thoughts really begin to twist. Because for a black hole to exist this early, and at this scale, it either had to start out enormous or grow with impossible speed. And that challenges more than just star formation models. It challenges how we think matter behaves in the earliest epochs of the cosmos. Theories float past you like drifting paper boats, ideas about direct collapse, about primordial clouds that bypass stars entirely and fall straight into gravitational wells, creating instant giants. But none of it feels solid. None of it explains how so many of these things appear at once, as if black holes were just a normal part of the cosmic starter kit. And then you notice something even stranger. These early galaxies, chaotic and energetic as they might be, are surprisingly well behaved. You were expecting irregular blobs, clumps of gas and stars thrown together like toddler art projects. But some of them are disks, thin, elegant spirals already in motion, already balanced, already holding their shape against the chaos around them. You watch one turn slowly, like a vinyl record on an ancient player. It's not wild, it's not messy, it's composed. You float closer. The stars here move in a rhythm, a quiet swirl that speaks of gravity and time working in harmony. It looks like something that should have taken billions of years to settle into form. And yet here it is, composed of starlight older than any human memory, rotating with grace in a universe still stretching its legs. This breaks your sense of chronology. Not just the facts, but the feeling of the universe's growth. These galaxies, so many of them, aren't just early, they're mature. They've been through things. They have structure metal order. They've survived starbursts. They've been shaped by black holes, and some of them have already stopped changing. You begin to suspect that maybe it's not just the galaxies that are unusual, it's your understanding of time itself. Because if galaxies are aging before your eyes while the universe is still in its first breaths, then maybe the pace of everything needs to be recalibrated. Maybe time isn't flowing evenly. Maybe our models have been too tied to human scales of age and distance. Out here, time pools in strange places. It folds, it leaps. You drift back from the galaxy now, almost respectfully. It feels like leaving an ancient city, one that shouldn't exist yet, filled with monuments that whisper of a forgotten history. And as you glide back into the darkness, the question follows you like a soft gravitational pull. What else out here has grown up before its time? The silence out here is thick with questions. You're still drifting backward away from the galaxy that aged before its time, but your mind hasn't caught up. It clings to the idea that something somewhere has gone off script. These early mature galaxies, heavy with stars carved by black holes, even hosting well-behaved disks, they don't just challenge one part of our understanding. They nudge at everything. Formation, evolution, even the very tempo of cosmology. And now, like a stone skipping through dark water, your thoughts land on a deeper uncertainty. What if it's not the galaxies that are wrong, but the foundation beneath them? Time, as you know it, is supposed to be reliable. Light moves at its constant pace. The expansion of space can be modeled, stretched, measured. And yet the moment you look into the earliest reaches with JWST, the illusion of a clean linear narrative begins to buckle. You pause near a veil of faint starlight photons so old they feel brittle, and consider what's really being measured. Redshift, that stretching of light over time, has always been your proxy for age, for distance, for cosmic sequencing. But redshift is only as trustworthy as the assumptions underneath it. Some cosmologists, late at night and off the record, wonder if the redshift-distance relation might not be as straightforward as we once thought. What if something's distorting it? What if the very structure of space-time is more layered, more fractal than our math accounts for? You glance at the idea not directly because it's slippery, but like a peripheral shadow, it lingers. Maybe space doesn't expand smoothly. Maybe it undulates. Maybe time in the early universe flowed through valleys and ridges, pooling here, surging there. You coast through a region of diffuse hydrogen, watching it shimmer faintly in ultraviolet whispers. This is supposed to be the raw canvas from which structure emerges, cool, neutral, formless. But even here, JWST has glimpsed irregularities. Pockets of heat, hints of early ionization, bubbles that shouldn't yet exist. These are clues, you realize, of something stirring too soon, something lighting up the void ahead of schedule. Reionization, that great cosmic transition, when starlight tore the fog from the universe's eyes, was supposed to be gradual. But JWST sees sharp fronts, abrupt awakenings. Galaxies that don't wait politely to shine. A sky that lights up in waves, not ripples. The thought lands heavily. What if the timeline of reionization itself is wrong? It's not just about starlight anymore. It's about the order of events. In the standard picture, the universe cools, neutral atoms form, and darkness reigns until gravity gradually builds the first lights. But what if those lights came on all at once, in a surge, rather than a slow burn? What if something catalyzed the entire process, igniting stars in multiple regions simultaneously, like a network of cosmic switches flipped in unison? You float in the imagined geometry of that idea, a lattice of nascent galaxies all blinking on like fireflies in sync. There's a beauty to it, but also a tension, because if the early universe was this interconnected, this coordinated, what caused that standard models rely on randomness, on density fluctuations, stretched by inflation, amplified over time. But coordination, that implies something deeper, something structured. A whisper brushes past your ear, or maybe it's just the soundless hum of a theory trying to take shape. Some physicists have toyed with alternatives to dark matter or dark energy that could allow for earlier structure formation. Others muse about hidden forces, scalar fields left over from inflation, still echoing through the fabric of space. You consider one such possibility, a fifth force acting only in the early universe, briefly accelerating the clumping of matter before fading into silence. There's no proof, but there's room. Out here, you're surrounded by room. Infinite, in fact. And within that vastness, the question of how galaxies form blends with where they form. Because as JWST scans deeper, it doesn't just find more galaxies, it finds more variety. Some regions teem with early giants, others are almost empty. The distribution feels uneven, almost patchy, as though the ingredients of the cosmos weren't stirred quite evenly. And maybe they weren't. You glide past a dense proto-cluster galaxies forming in tight proximity, as though drawn together by some unspoken pact. Their lights echo one another, their masses align. It's too early by standard estimates for such coordinated structure. Protoclusters like this shouldn't form until much later, long after galaxies have matured. But here they are, weaving together in the young dark. You drift through their nascent corridors, imagining what they'll become: superclusters, filaments, the spine of the cosmic web. And yet here again, something is off. These structures, observed so soon, imply that the seeds of complexity were planted far earlier than models allow. Gravity works slowly. It's persistent, but patient. For matter to gather like this, so fast would require a head start, or a cheat code. You squint at the notion of primordial non-uniformity, the idea that the early universe wasn't quite as smooth as inflation predicted. That perhaps quantum fluctuations weren't evenly stretched, that some regions inherited more gravity, more potential, more destiny than others. If that's true, then the map we've been using, the one that says all of space-time emerged from a single uniform expansion, might need edits. You ease backward, further still, past the edge of current data, into regions JWST hasn't yet reached. Here it's pure speculation, a realm of quiet potential. But the echoes of what you've seen carry with you. Galaxies form too fast, black holes, too big structures, too early starlight too synchronized. It adds up to more than surprise. It adds up to a paradox of timing. And like all paradoxes, it invites revision. The kind of revision that keeps cosmologists awake at night, blinking at equations that no longer comfort them. Maybe the universe is older than it looks. Maybe it's more connected. Maybe time flowed differently near dense regions, or matter interacted through forces we've only begun to sense. Or maybe, just maybe, the very assumptions we've made about beginnings need to bend. You drift on, not with answers, but with a widening sense of awe. The universe isn't smaller than we thought. It's more intricate, more mischievous, more alive in its early chapters than anyone dared guess. And for now, that's enough to carry you forward. Time stretches out behind you now, like a wake of tangled threads, stars too old, galaxies, too calm structures too soon. But you're not turning back. The questions tug you forward into deeper shadow. As you slip farther from the known, the light begins to shift. It becomes thinner, more strained, like it's remembering the long journey it's taken to reach you. And in that strain, in those elongated photons, you begin to sense something stranger still, a tension, not just in what we see, but how we see it. You've heard that telescopes like James Webb look back in time, and it's true in the poetic way people mean it. But what does that really imply? You're not just peering through space. You're intercepting the memory of light. You're unspooling a reel of ancient footage, each frame warped by the curvature of expanding space. And the further back you go, the more uncertain your grip becomes, not because the signal fades, but because the very context unravels. For decades, cosmologists thought they had the stage directions figured out. The early universe was hot, dense, chaotic. Then inflation smoothed it out. Gravity took over. Stars lit up, galaxies formed, and the show went on. But Webb has peeled back the curtain on Act 1, and the choreography is all wrong. Structures aren't just appearing earlier, they're appearing everywhere in numbers that make the script look like a rough draft. You pause beside a grouping of compact red dots, distant galaxies whose light took over 13 billion years to reach us. Each dot a fully formed city of stars. The density of them is striking. They're not isolated specks in an otherwise empty canvas. They cluster, congregate, hint at a richness we weren't expecting so soon. And the problem isn't just their age, it's their abundance. There are too many of them. Models predicted a gradual build-up, a few early galaxies sprinkled here and there, ramping up as time moved forward. But Webb keeps finding them by the dozen. Some estimates suggest there are 10 times more galaxies at high redshifts than expected. That's not a rounding error. That's an existential oops. It's like arriving at the first chapter of a book and finding it already filled with footnotes, plot twists, and an entire supporting cast. So you float between them, wondering what allowed this early profusion. Was it a miscalculation in star formation efficiency? Did the first halos of dark matter collect gas faster than we thought? Maybe the rules for early starbirth were different, more violent, more fertile. Or perhaps something entirely new was happening, a regime of physics we don't understand kicking in during those first few 100 million years, like a backstage crew we never noticed. There are whispers of exotic possibilities. Some physicists quietly propose changes to the initial mass function, the statistical recipe for how many small versus massive stars form. If the early universe favored bigger stars, everything would evolve faster. More light, more heat, more metals, more black holes. But also, more radiation, more pressure, more ways for everything to blow itself apart before it had a chance to settle. You glance toward a particularly bright galaxy, one with a suspected active black hole at its core. Its light pulses faintly in infrared, wrapped in swirling dust. This one, researchers say, might be lensing a background object, warping the light of something even farther behind it. That's another wrinkle. Gravitational lensing can make galaxies appear brighter or more massive than they really are. So what if some of these ancient giants are illusions, optical sleight of hand from massive objects between us and them? But even when accounting for lensing, the numbers remain stubborn. Too many galaxies, too much structure, too fast. You feel like you're watching an orchestra come together for its opening piece, except everyone's already in tune, the conductor has skipped rehearsal, and the first notes are a flawless crescendo. It's beautiful and deeply suspicious. A quiet joke echoes through your thoughts. Either the early universe was on caffeine, or we've missed something fundamental. And it wouldn't be the first time. Science thrives on correction, but it stumbles sometimes over its own assumptions. We've built elegant models, lambda CDM, the cosmic microwave background, the inflationary paradigm. But we've also filled in gaps with educated guesses. Necessary ones maybe, but still guesses, like dark matter. You drift near a simulation, a swirling map of dark matter, halos invisible but inferred, guiding the formation of everything luminous. For galaxies to form as early as we see them, these halos must have collapsed fast and deep. But dark matter doesn't interact with itself or with light. It only clumps through gravity. So unless gravity behaved differently early on, something had to help. Or more daringly, what if dark matter isn't as passive as we thought? There's a theory still whispered, like a conspiracy among cosmologists, that early dark matter might have cooled and clumped more efficiently than expected. Maybe it interacted through its own dark forces, invisible cousins of the electromagnetic or nuclear interactions we know. If dark matter formed dense seeds faster, that could explain the early galaxy boom. But it opens up a rabbit hole of new physics, entire realms of particles we've never detected, forces that don't touch light but shape the universe from the shadows. And yet, you don't feel fear, just curiosity. This is how discovery works. You press your face to the glass of the cosmic aquarium, watching creatures no one expected thriving in the depths. It doesn't invalidate everything we know. It just tells us that the map is incomplete. And the best part, the universe doesn't mind. It just keeps spinning, birthing, burning, evolving, whether we understand it or not. One of the galaxies ahead suddenly blinks. A supernova perhaps, or a variable star flaring in infrared. You catch the flicker and feel its time-lagged heat ripple through your thoughts. That light left its home when the universe was barely waking. And now it touches you. You smile just a little. Out here, it's easy to forget how far we've come. From stone tools and cave fires to billion-dollar telescopes decoding the baby photos of creation. And still, the story resists being finished. You drift on gently into the growing silence between galaxies, the spaces that Webb hasn't yet touched. They don't feel empty. They feel pregnant with possibility. The emptiness ahead isn't absence, it's invitation. A hush deep and velvet stretching beyond the galaxies Webb has managed to glimpse. You drift into it without resistance, letting your thoughts unravel and float alongside you. Out here, the light is thinner still, like the last fading embers of a campfire you didn't start. And yet the further you go, the more certain you feel of one thing. We are not just missing details, we may be misreading the entire tempo of cosmic history. You've seen the headlines, galaxies too early, black holes too big, cosmologists baffled, and behind every splashy title is a quiet truth no one wants to say too loudly. The standard model is stressed, not broken, not wrong, just stretched. Like a well-worn sweater tugged in too many directions by data that no longer fits as neatly as it once did. And nowhere is that tension more palpable than in the mismatch between early galaxy formation and cosmic expansion itself. It begins with Hubble. Not the telescope, though, that one has served well, but the constant. The rate at which the universe expands. Measured in kilometers per second per megaparsec, it's meant to be a simple yardstick. One number to describe how space stretches with distance. But lately this number has split in two. The local universe measured through nearby supernovae and galaxies gives one value. The early universe measured from the cosmic microwave background gives another. And the difference is not small. You hover at the edge of this tension like watching a seesaw stuck at a tilt. Scientists have debated every possibility: observational errors, calibration issues, missing physics. But none of the usual suspects seem guilty. Instead, the discrepancy known casually as the Hubble tension persists. And here's where it gets curious. If early galaxies are forming faster, shining brighter, and clustering sooner than predicted, that might not just be an issue with galaxy models. It might hint at something deeper, a different rate of expansion in the early cosmos. You spiral gently through that idea, letting it settle like dust in zero gravity. Maybe the universe expanded faster early on, slowing down more quickly than expected. That would allow structures to form sooner, to mature, while the rest of space caught up. But it contradicts the current picture, where dark energy gradually accelerates expansion over time. So how could it have slowed before speeding up? Some physicists suggest there was an early dark energy field, a brief invisible pressure that swelled the cosmos right before recombination, then faded away, like a cosmic hiccup. This extra energy could have altered the spacing between early matter clumps, skewing our interpretation of the CMB and helping resolve the Hubble tension. But it's still speculative, a ghost of a field we can't directly see. And even if true, it wouldn't explain everything we're seeing with JWST. You pass by a filament of warm dust glowing faintly with the relic heat of ancient stars. Within it, galaxies hide like pearls in smoke. These dusty galaxies, bright in infrared dim, invisible light, have been cropping up earlier than expected. And they complicate the picture. Dust requires time to form. You need multiple generations of stars to forge heavy elements, for those elements to clump cool and spiral into grains. So why is there so much dust so soon? Maybe those first stars were more efficient than we thought. Maybe they lived fast and died young, enriching their surroundings with carbon-silicon iron. Or maybe star formation itself isn't as gentle a process as we've modeled. Some simulations hint that early galaxies could have undergone bursty formation, intense episodes of rapid star birth, followed by feedback-driven quenching. You imagine galaxies flickering like candles in a breeze, brightening and dimming their growth, uneven but accelerated. Still, the dust lingers, and with it, the idea that our timeline is warped. You begin to wonder, is time itself behaving differently in different regions? General relativity allows for gravitational time dilation. Clocks tick slower in stronger gravitational fields. Could this explain part of the discrepancy? If early galaxies sat in deeper wells of matter than expected, their clocks would appear to us as running slower, even as they evolved quickly in their own frame. The thought is tantalizing. It doesn't rewrite physics, it leans into it. Maybe we're not seeing galaxies maturing too fast. Maybe we're just watching them from a high perch, looking down a well of gravity and misunderstanding their rhythm. But even this doesn't quite resolve the scope of the problem. You drift past a simulated timeline, projected like a thread of light from your wrist to the edge of the void. The line bends and curves with possibility. Every bump represents a shift in theory, a tweak, a patch. But even as the timeline writhes to fit the new data, you sense a deeper unease. What if the patchwork won't hold? What if we're trying to shoehorn a fundamentally different cosmos into an old frame? A quiet laugh escapes you. Just air and static, really. The joke's on us, you think. For so long, we treated the early universe as a blank slate, a place where initial conditions simply were and everything else followed like dominoes. But what JWST shows is that the early universe is not a child. It's already a teenager, moody and complicated, keeping secrets and leaving cryptic signals on our doorstep. You pause, momentarily suspended in a void between galaxy clusters. Ahead, a thin wall of faint starlight arcs across space, a structure forming faster than it should, too synchronized for comfort. It resembles the bones of a cosmic wall, not just random clustering, but alignment. And this perhaps is the most unsettling whisper: the early universe is not as chaotic as we thought. There is structure in the storm, Some scientists have begun wondering if inflation, our best guess at what smoothed the universe in its first sliver of a second, was more irregular than advertised. Perhaps inflation wasn't a uniform ballooning of space, but a jagged expansion producing pockets of different energy densities that would leave behind regions of faster evolution, faster structure, and perhaps faster clocks. Of course, this is just one idea among many. Maybe it's wrong. Maybe they all are. But the uncertainty isn't frightening. It's beautiful. You realize drifting here that we are witnessing science in motion. Not the polished answers of textbooks, but the murky magical edge where data meets wonder. You lean into that edge weightless and unmoored and let the tension carry you. There's no final conclusion yet, only a trail of light leading deeper into mystery. You drift beyond the last wall of light and into something quieter, an unlit ocean between epochs where photons are scarce and speculation hums louder than certainty. The silence here isn't peaceful. It's expectant, like the pause between movements in a symphony when even the air holds its breath. But this too is part of the story, because in this deep stillness lies one of the strangest questions of all. How did black holes, those paradox factories, those cosmic exit wounds, form so early and grow so monstrously large? You ease into the thought, gliding alongside an invisible beast, a supermassive black hole, 10 billion solar masses, strong hiding at the center of a galaxy, barely a few 100 million years old. It's one of many that Webb has spotted indirectly their gravitational pull, lighting up gas and dust like warning flares. And here's the rub, there simply hasn't been enough time. According to the rules we thought were firm black holes, begin small, maybe from the core of a massive star, collapsing under its own weight. From there, they grow slowly, feeding on surrounding matter over billions of years. But what we're seeing suggests a different pace altogether. These early monsters didn't start small. Or if they did, they skipped the awkward middle phase and bulked up with suspicious speed. There are a few guesses. One involves direct collapse black holes, giant gas clouds so dense and hot that they skip stars entirely and implode straight into black holes weighing tens of thousands of suns. It's efficient, convenient, and still mostly theoretical. Another proposes that the early universe had unusually massive stars, hundreds of times more massive than our sun, that collapsed into hefty seeds. But even those seeds shouldn't have had time to grow this much this fast. You glance toward a glowing region, an active galactic nucleus, its central black hole devouring matter and belching out radiation. The jets are faint from here, just whispers in the infrared, but they carry clues. If accretion was more aggressive in the early universe, perhaps aided by dense gas environments, maybe black holes could balloon rapidly. But there's a limit called the Eddington limit to how fast a black hole can safely grow without its own radiation pushing material away. And yet these early behemoths seem to have laughed at that rule. Some researchers suggest they may have grown in short, violent bursts, super Eddington accretion brief episodes, where feeding outpaced physics and matter poured in faster than expected. Others wonder whether mergers between early black holes sped up the process. You imagine two seeds spiraling into each other, their gravitational waves echoing out like invisible screams, fusing into something new and ravenous. But even so, the numbers don't add up easily. The paradox feels familiar now, like a note that keeps playing just off-key things appear too soon. Galaxies, dust-heavy elements, black holes, everything seems to leapfrog the standard timeline. And maybe, just maybe, that means the timeline itself is warped. You linger here watching the black hole's invisible mass warp space, like a dent in a rubber sheet. Stars curve gently around it like dancers caught in a slow whirlpool. It's elegant and disconcerting, because black holes don't just challenge astrophysics, they challenge meaning. They sit at the intersection of gravity and quantum mechanics, where time breaks down and information vanishes, or at least hides in a form we don't yet comprehend. And now their early presence pulls at the fabric of our cosmological assumptions. If they were here from the beginning or nearly so, then perhaps they didn't form after galaxies. Perhaps they came first. There's a radical idea, a fringe but fascinating whisper, that primordial black holes might be the answer. Formed not from stars, but directly from density fluctuations in the very early universe, before light itself had room to breathe. If true, they could serve as seeds for galaxies shaping structure instead of being shaped by it. They could even, in some versions of the theory, account for some or all of dark matter. You let that possibility swirl around you like dark coffee in a nebula cup, invisible but heavy. Primordial black holes would turn our timeline upside down. Instead of galaxies forming stars which then collapse into black holes, we'd begin with the black hole's silent ancient sentinels around which matter coalesces and stars are born. They'd be the scaffolding of structure, the cosmic bones. It's speculative, sure. Most physicists aren't ready to buy the idea wholesale. But then again, most physicists weren't expecting to find supermassive black holes already roaring in galaxies 13 billion years ago. Reality, it seems, is less interested in our caution than we are. Still, as you drift beside these early giants, you can't help but feel a kind of awe. They don't care whether they make sense to us. They just are, lurking in the fog of creation, defying chronology, swallowing questions along with everything else. And perhaps the most important thing they're feeding is our humility. There's something gently ironic about this whole situation. We built a telescope so powerful, so precise, that its very success has forced us to question the foundation we built it upon. That's science for you, not a ladder of certainty, but a spiral staircase that sometimes loops back on itself, offering the same view from a deeper place. You look again at the black hole, now fading into distance, its influence still rippling outward. Around it, stars continue to form, gas continues to swirl, galaxies continue to grow, and you realize that the puzzle doesn't diminish the beauty, it is the beauty. The universe is not a solved equation. It's an unfolding poem with stanzas written in gravity and light. Somewhere ahead, perhaps, is a better model. One that makes room for these early giants. One that includes the forgotten variables, the overlooked processes, the quantum whispers we've yet to hear clearly. But until then, the tension remains. A good kind of tension. The kind that keeps curiosity awake long into the night. And here in the silence beyond sight, you let that curiosity wrap around you like a gravity well. Not crushing, but anchoring. Reminding you that there are questions even a $10 billion telescope can't answer yet. And that's exactly why we built it. The deeper you float, the older the silence becomes, not quiet, like a room with no sound, but like the silence between ancient waves long after the tide has receded, the kind of silence that remembers. Out here, the galaxies begin to thin, not in number, but in clarity. Their light, stretched by time and distance, no longer arrives as brightness, but as a kind of echo, a sigh across space, distorted and red. You find yourself brushing against the oldest light. There is the cosmic microwave background. Not with your hand, of course, but with your thoughts, like fingertips tracing the texture of the void. This light is not from galaxies or stars. It's from before those things. It's from when the universe was just 380,000 years old, a dense hot plasma that finally cooled enough to let photons travel freely. That moment, known as recombination, is our farthest direct glimpse into the past. But what lies beyond that wall of light? You can't see it, not yet, not with any telescope, but you can feel it press against the limits of knowledge like a locked door with warm light seeping underneath. And the funny thing is, we thought we understood what lay behind it. Inflation. A brief moment when the universe expanded faster than the speed of light, smoothing everything out like a wrinkle-free shirt of space. It's a lovely idea, elegant and helpful. But now, just like with galaxies and black holes, the data is starting to raise its eyebrows. Because here's the twist. If early galaxies are too advanced and early black holes too massive, then perhaps it's not just the expansion that needs revising, but the very initial conditions of the universe. You drift backward in time, mentally peeling away layers of matter and radiation, past star formation, past recombination, into the era of quantum fluctuations and inflationary fields. And here things get murky. We used to think inflation was a simple single-field event, a scalar field rolling downhill, smoothing space as it went. But the cosmic microwave background, when examined closely, holds subtle anomalies, tiny asymmetries, cold spots, alignments that shouldn't be there, like brushstrokes that don't match the rest of the painting. Some cosmologists refer to one of these features as the axis of evil, not because it's dangerous, but because it breaks the expected symmetry of the CMB across the sky. It's not just a statistical blip. It suggests that the early universe may have had a preferred direction and orientation. And if that's true, it violates the principle of isotropy, which says the universe should look the same in every direction. A small thing, perhaps, but small things have a way of unraveling big ones. You float through the echo of that earlier symmetry, now passing through its suggestion like a ghost ship through fog. No sound, just a nudge, a memory in the data. And you begin to wonder, what if inflation wasn't uniform? What if the early universe was already structured in ways we haven't fully grasped? Could these structures, these subtle fingerprints, be responsible for the strange maturity we're seeing in early galaxies? One idea, still young and a bit rebellious, is that the early universe may have experienced anisotropic inflation expansion that wasn't the same in all directions. Imagine a balloon stretching faster along one axis than the others. It would create a universe that appears uniform on large scales, but hides directional preferences in the fine print. These preferences could seed variations in density, and variations in density in turn could accelerate the formation of early structures. The possibility makes your thoughts ripple like photons grazing the edge of a gravitational lens. If true, it means the beginning wasn't quite as blank as we thought. That maybe something, some field, some fluctuation, some cosmic leftover, carried a pattern from before time as we know it. And that brings you gently and inevitably to a more radical possibility. A whisper you've likely heard before, dismissed, maybe laughed at, until now. What if the universe we see is just a bubble, one among many? A pocket of inflating space that stabilized into what we call reality, while other regions inflated into their own disconnected realms. It's not just science fiction. It's called eternal inflation, and in some versions it's a feature, not a bug. Different regions of space stop inflating at different times, creating bubble universes with different properties, different laws. Our universe then could be just one leaf in a very big forest. And perhaps what we're seeing, these unexpected early galaxies, these monster black holes, these possible asymmetries, are local quirks of our bubble, statistical oddities in a multiversal sea. You might smile at the thought, or wince. It's an uncomfortable idea. We build physics to be universal after all, not provincial. But if cosmic inflation is eternal and our observable universe is just a patch, then perhaps the tension between theory and observation is not failure, it's context. Still, even in this big picture, questions remain. Why does our bubble look the way it does? Why these constants, these particles, these dimensions? And why now, right now, are we able to look back and find these cracks in the frame? You slow again, drifting beside a faint filament of early structure. It's hard to see, almost not there at all, but it connects galaxies like beads on a cosmic string, stretching across space in a delicate net. This web, this early architecture may hold the answer, or at least the next clue. Because it's not just that galaxies exist too early, it's that they exist in the right places, aligned along filaments and nodes that suggest order deeper than gravity alone. Some fringe theories even suggest that space itself may be emergent, a product of quantum entanglement with geometry arising from information networks at the smallest scale. In that view, what you're floating through isn't space at all. It's an illusion, a macroscopic result of microscopic logic, like watching ocean waves and forgetting they're made of molecules. You exhale out of habit, not need. The idea is too big to hold, so you don't. You just let it pass through you, a comet of possibility on a hyperbolic trajectory. The cosmic microwave background recedes behind you now. Not gone, just folded into the distance like a postcard from your childhood. Ahead lies a deeper darkness, still untouched by light. A region where theory wanders without a map. But even here in the most ancient silence, there is something else, a sense that the universe is not just old, but haunted by memory. And memory, as you're beginning to learn, is never neutral. It whispers, it distorts, it leads you forward with half-truths and riddles. The kind of riddles that start with a telescope and end with a mirror. You now find yourself floating in a quieter, stranger space, a kind of cosmic backstage, where the floodlights of starlight haven't yet risen, and the stagehands of matter are still deciding where to place everything. Here, you're not surrounded by blazing galaxies or ravenous black holes. Instead, you drift through the pregnant pores before form the dark matter scaffolding that underpins it all. You don't see it, of course. No one does. But you feel its presence like the weight of a thought just before you speak. Dark matter is everywhere and nowhere. It doesn't shine. It doesn't clump into stars. But it shapes the dance, like a conductor in a soundproof booth, invisible yet utterly in control. And here's where things get even more peculiar. The galaxies that Webb has found, those impossibly early, well-formed islands of light, aren't just showing up too soon. They're showing up in places that suggest the dark matter got a head start. It's as though the invisible framework was already exquisitely sculpted, primed for rapid structure to fall into place. The problem. According to the standard cosmological model, yes, the same one with its neat acronyms and elegant curves, there simply hasn't been enough time. You think back to LCDM lambda cold dark matter, the reigning theory, the good enough model. It says dark matter is cold, not temperature-wise, but slow-moving, allowing it to clump. And it says the universe is dominated by this stuff, with dark energy, the lambda driving the accelerated expansion of space. It works well mostly, but Webb's data is poking it in the ribs. Because if galaxies were already forming in large numbers a few 100 million years after the Big Bang, that implies their dark matter halos the invisible cocoons that shepherd baryonic matter into becoming galaxies must have formed even earlier. But how early is too early? You hover beside a simulation, now not a galaxy, a digital model of the early universe running like a clock made of equations. These simulations, complex, beautiful, predict when and where the first dark matter halos should appear. They tell us how large they should be, how fast they should grow, and in almost all of them, the kind of galaxies Webb is seeing just shouldn't exist yet. They're too big, too bright, too well behaved. It's like finding skyscrapers in a village that just finished laying roads. Some researchers are doubling down, refining the simulations, tweaking parameters, stretching models like cosmic taffy to see if there's wiggle room. Maybe dark matter was slightly warmer. Maybe baryonic physics, the physics of the ordinary matter we can see, acted in ways we've overlooked. But others are beginning to whisper something more radical. Maybe we're not dealing with cold dark matter at all. You glide past a theory now softly illuminated by controversy. Fuzzy dark matter, a form of dark matter made of ultralight particles so light that their quantum wavelengths stretch across entire galaxies. Imagine that matter that doesn't act like grains of sand, but like ripples on a lake. In this model, dark matter resists clumping on small scales. It blurs the sharpness of gravity, smoothing the universe's structure in a way that could help explain certain galactic features we've observed, but also perhaps mislead our expectations about early formation. Then there's self-interacting dark matter, a twist that suggests dark matter particles don't just float silently past one another, but occasionally bounce, tangle, or exchange momentum. This could influence how halos form and merge, possibly accelerating the development of early structure if the interactions were just right. It adds a kind of social awkwardness to dark matter's character, which is admittedly kind of charming. And of course, there are whispers, always whispers, about whether dark matter exists at all. You hesitate at that edge. It's dangerous territory, but sometimes it helps to glance down. Modified gravity theories like MOND, modified Newtonian dynamics, or even more exotic proposals suggest that what we interpret as dark matter might actually be a sign that we've misunderstood gravity itself. That Newton's and Einstein's laws, so elegant in the solar system, start to fray at the galactic and cosmic scale. It's a bit like watching a clock and insisting it's broken because the hands move funny, when in fact the gears inside might follow rules you haven't yet invented. But even if you keep dark matter whatever its form, you're still left with one of the deepest riddles. How did it organize itself so quickly? The standard timeline is becoming like a novel with pages missing in the first chapter yet, with fully developed characters already giving eloquent monologues by page 10. You drift back toward a Webb image, deep and subtle, where galaxies cluster along filaments, their forms faint but unmistakable. These structures, in a sense, are maps of the dark matter beneath them. Gravitational wells dug by invisible hands, but they also feel intentional. Not in a mystical sense, but in their clarity. Like someone solving a jigsaw puzzle at impossible speed. And you can't help but wonder, what if dark matter isn't just a passive stagehand? What if it's an active agent in the universe's development? Some theories, still speculative, propose that dark matter may couple ever so slightly with other fields, or even with the curvature of space itself, that it may have hidden dynamics, internal pressures, decay, channels, whispers of complexity beyond its cold and dumb reputation. These are not mainstream ideas, but neither were early galaxies the size of the Milky Way shining like lighthouses when Webb switched on. You find a strange comfort here, in the not knowing, in the gentle collapse of certainty. Because this is what discovery really feels like, not answers, but questions with better lighting. And Webb, bless its golden honeycomb heart, has given us a flashlight that pierces the most ancient fog. Still, you can't help but feel the scale of the problem. We're not just revising our understanding of a particle or two. We're rethinking the architecture of everything. From halos to hierarchies, from cold to fuzzy, from passive to interactive. It's like realizing the scaffolding of your house is made of mist, and still the walls are standing. And somewhere, just at the edge of your mind, another possibility flickers, that what we call dark matter is not a single thing, but many. A family of particles, or fields, or even entirely new sectors of physics' hidden realms that interact only through gravity, the quietest force whispering their influence across cosmic distances. You exhale again, not because it brings clarity, but because it doesn't. And that too is part of the beauty. You drift now through a deeper void where galaxies become sparse again, not because there are fewer of them, but because your gaze has shifted away from the bright clusters and into the voids between them. It's not an emptiness exactly, it's more like negative space in a painting, the quiet between brushstrokes. These great cosmic gulfs, vast and haunting, are just as much a part of the universe's structure as the luminous arcs of stars. And yet, even here, things aren't quite behaving. You've followed the trail of those early galaxies and their mysterious birthplaces, and now you arrive at a tension much closer to home, the Hubble tension. A disagreement so persistent, so stubborn, it now sits like a splinter in the heart of cosmology. At its simplest, it's this: when we look at the early universe, say the cosmic microwave background, we get one number for how fast the universe is expanding. But when we measure that same rate using nearby galaxies and supernovae, we get a faster number. Not just a tiny mismatch. A stubborn, repeatable, statistically significant one. It's the kind of disagreement that makes scientists uncomfortable. Because it doesn't go away with better data. It gets worse. You coast alongside a thought maybe the early universe and the present day one are playing by slightly different rules. Or maybe we've missed something fundamental about how expansion unfolds over time. One possibility, elegant in its ambition, is that dark energy, the mysterious force driving the universe's accelerated expansion, is not constant after all. The cosmological constant, once introduced by Einstein and then famously discarded, might have been right in name, but wrong in spirit. Maybe this force evolves over time. Maybe it had a different strength in the early universe, nudging galaxies into place more quickly, before softening into the gentler push we observe now. It's not just speculation. Some models, like early dark energy, suggest that this mysterious substance flared briefly like a match struck in a dark room before fading into the background. This brief flare could reconcile the two different expansion rates. It would accelerate early growth, helping those baby galaxies blossom while still matching our current measurements. The math is delicate, the parameters narrow, but the idea is captivating. You lean into the idea, and the void around you trembles just slightly, because even the emptiest places are still full of mystery. The energy density of the vacuum itself, what we sometimes call the cosmological constant, has always been one of the most baffling numbers in all of physics. Theoretically, it should be enormous. Off the charts, enormous. Yet in reality, it's vanishingly small. Not zero, but so tiny compared to predictions that it feels like the universe is whispering a joke you're not quite ready to get. This mismatch, often called the cosmological constant problem, is one of the great embarrassments of theoretical physics. It suggests that something is deeply wrong, not just with the models, but perhaps with how we even ask the questions. And so the void you drift through now isn't just a physical one. It's conceptual. It's the space left behind by confusion, the chasm between observation and expectation. It's oddly peaceful here, like being lost in a library where none of the books match their titles. And you can't decide whether the catalogue is wrong or the language has changed. Still, not everyone agrees. The Hubble tension is a crisis. Some argue it's just a calibration issue, something mundane like a faulty ruler or an overlooked bias in the data. Others insist it's evidence of new physics waiting just beyond the veil. You float past these ideas like leaves on a cosmic wind. Early dark energy, phantom fields, modified gravity, hidden neutrinos, variable dark matter interactions. Even time itself, linear, sacred, and supposedly constant, is under quiet review. Because if time runs differently in different epochs, then maybe the mismatch isn't in our measurements. Maybe it's in our assumptions. One fringe idea suggests that time itself might emerge not as a fixed backdrop, but as something that crystallizes out of more fundamental timeless laws. A phase transition, like water freezing into ice. In this view, early cosmic time might behave differently, not in metaphor, but in math. The seconds themselves may have been shorter, the tick of the universal clock inconsistent. And if so, then expansion itself may have unfolded under rules we don't yet understand. You can't help but smile at the audacity of it, that something as basic as comforting as time might be part of the illusion. But the Webb data, stubborn and glowing, doesn't really care what makes you comfortable. It shows what it sees. And what it sees again and again are galaxies that shouldn't be there yet, expanding in ways that don't quite add up. Maybe you think this is what scientific maturity feels like, not certainty, but comfort with doubt. The willingness to accept when the universe is outpacing your equations. The irony, of course, is that we've been here before. You recall the story of Neptune, when astronomers noticed that Uranus was wobbling in ways Newton's laws couldn't explain. They didn't throw out Newton. They inferred an unseen planet Neptune whose gravity was tugging at the edges of what was known. And they were right. But just a few decades later, when Mercury's orbit also misbehaved, they tried the same trick again, looking for a hidden planet called Vulcan. This time, the planet didn't exist. The solution wasn't another object, but a new theory entirely, general relativity. So now you ask, are we in a Neptune moment or a Vulcan moment? Is the tension a clue that something new is lurking out there? Some particle, some interaction, some twist in the vacuum? Or is it a sign that the very foundation of cosmology needs revising, that our best theories are brushing up against their expiration date? You feel the weight of both answers. And in this silent place, you also feel the humility of not knowing. The dark sky above you is filled with light from billions of years ago, and still it's not enough. Not yet. We are, after all, children of a young species, staring at a puzzle older than Earth, using instruments we built with stardust and stubbornness. But the fact that we're even here asking these questions, standing at the event horizon of understanding, that's something. That's everything. Now, with the questions piling higher than the stars, you drift into a softer light, a golden web stretched across nothingness. You're hovering over what might be the most profound contradiction of all, that these galaxies, blooming far too early in cosmic history, are not chaotic or malformed as one might expect from rushed beginnings. No, they're structured, elegant, spiral arms curled like seashells, bulges dense with stars, disks spinning with gravitational grace. And that's the part that makes scientists squint. Because this isn't just about early galaxies, it's about how well behaved they are. You would expect the earliest galaxies, those forming just a few 100 million years after the Big Bang, to be messy toddlers bumping into things, forming stars too quickly, collapsing under their own weight. But some of the galaxies James Webb is spotting look mature, confident, as if they've been at this for a few billion years, not a few 100 million. You think of our own Milky Way, a middle-aged beauty. It took eons to reach this kind of structure. Stars formed and died, gravity sculpted and resculpted. So how are these baby galaxies already built like adults? The usual model of galaxy formation, the one that's lived in textbooks for decades, describes a slow process. Clouds of gas collapse into stars. Stars gather into clusters. Clusters into galaxies. It takes time for disks to form, for rotation to settle, for chaos to cool into order. But Webb's early galaxies are skipping steps. They're like someone starting a novel on chapter 9 and already writing in perfect calligraphy. You glide deeper into the honeycomb of a distant galaxy's image. It's not just a smear of light. It has symmetry arms, a bright nucleus, details that shouldn't be possible so early. And yet there it is. This raises an unsettling question. Is our model of galactic evolution broken? Or has the universe just been extra efficient in ways we haven't accounted for? Some astronomers propose that the universe might have gone through a period of extremely rapid star formation, where dense pockets of gas turned into stars at breakneck speed. That could, in theory, build massive structured galaxies earlier than expected. But there's a catch. Star formation at that pace tends to produce violent feedback, winds, radiation, and supernova explosions that tear galaxies apart before they finish assembling. And yet Webb is showing us galaxies that seem intact, calm, radiating light like they've been meditating for millennia. So maybe the conditions back then were different, colder gas perhaps, which collapses more easily and stays quiet longer, or higher densities, which could accelerate structure formation without ripping things apart. It's possible the primordial soup had a secret ingredient, something that made galaxy building smoother, faster, less messy. Something we haven't added to our recipe yet. Then again, maybe we're looking at a selection bias. Webb is, after all, a highly sensitive instrument. Maybe it's simply catching the most developed galaxies, the outliers. The best-case scenarios shining more brightly than the average. Perhaps there were still countless proto-galaxies bumbling around in the shadows, chaotic, unformed, too faint for even Webb to detect. Maybe we're mistaking the peaks for the whole mountain. But even that doesn't entirely explain what's being seen. Some of these galaxies are not just luminous, they're massive, 10 times the mass of the Milky Way packed into a much smaller volume, shining brightly in ultraviolet and infrared. That kind of growth requires vast reservoirs of gas-precise conditions and, most mysteriously, time, which they supposedly didn't have. So the whispers grow louder. Maybe these galaxies formed from primordial black holes acting as seeds. Or maybe early supermassive black holes, somehow forming even faster than the galaxies themselves, shepherded the surrounding matter into shape more efficiently than stars alone could. There's even a provocative idea floating in the minds of a few theorists that the initial conditions of the universe weren't as smooth as we thought. That inflation, the great rapid expansion that smoothed out the early cosmos, may have left behind hidden lumps, pockets of overdensity, like swirls in the batter of a well-mixed cake. And in these dense pockets, gravity would have had a head start, forming galaxies faster and earlier than elsewhere. But if that's true, then our entire picture of the early universe, the evenness of the cosmic microwave background, the neatness of the large-scale structure, may need revisiting. because it would mean that even the beginning wasn't as uniform as we believed. You pause, suspended in a moment of irony. The more precise our instruments become, the more they unearth these imperfections. The more we look for symmetry, the more asymmetries emerge. It's as if the universe is winking, reminding us that perfection was never the point. Still, not all galaxies are spirals. You see that too. Some of these ancient structures are spheroidal, like cosmic snow globes. Others are clumpy, irregular, halfway between chaos and grace. But even they seem further along than the models allow. It's not their shape alone, it's their star populations, their metallicities, their kinematics. Things you can't fake, not without time. It's like finding a village with advanced metallurgy, complex music, and multilingual poetry before they've even invented the wheel. So maybe structure is more of an emergent inevitability than we thought. Maybe under the right conditions, the universe rushes to complexity, skipping the long-winded steps we assumed were necessary. Like crystallization, like sudden snowflakes forming from chaotic vapor, perhaps galaxies fall into being faster than logic permits. Or perhaps our logic simply isn't yet fast enough to keep up. You let that thought sit with you. It's oddly comforting in a way that the universe is more eager to form beauty than we ever gave it credit for. You ride a soft current, now slower than light, quieter than time. It carries you along a thread between galaxies, between theories, between belief and bewilderment. You're starting to see the big picture, not in the sense of understanding it, but in recognizing just how large and uncertain it really is. For decades, the standard cosmological model, the tidy LCDM framework, has been our map. It's elegant in its way. It assumes that the universe is made of a few key ingredients: visible matter, which is charming, but rare dark matter, which outweighs the visible stuff by a factor of 5, but refuses to reveal itself, and dark energy, which dominates everything and behaves like a cosmic anti-gravity field. This model tells us that galaxies form inside halos of dark matter, which gather like invisible scaffolding in the early universe. The halos attract gas, the gas cools and collapses, and stars begin to burn. And this model works. It explains the structure we see today. It predicts the cosmic microwave background, the large-scale distribution of galaxies, the accelerating expansion of space. It's a masterpiece of theoretical physics, except when it isn't. Because here in the firefly shimmer of James Webb's gaze, we see things that don't quite line up. Galaxies that are too big too early, black holes that are too massive too soon, structures that shouldn't exist until billions of years later yet somehow do. It's not a total failure, more like a hairline crack in a stained glass window, one that becomes visible only when the light hits just right. The LCDM model is still useful, but it might be incomplete, like a recipe that assumes salt, pepper, and heat are enough to make a gourmet meal. And then someone tastes saffron, so now you float through a cloud of alternative theories. Some drift gently poetic in their ambition. Others churn like storms, shaking the foundations of accepted science. One of them whispers of modified gravity, the idea that gravity itself doesn't behave quite the way we think it does. Maybe Newton and Einstein were both right, most of the time. But on cosmic scales at very low accelerations, gravity might change character. It might weaken more slowly or curve in stranger ways, allowing structures to form faster without relying on invisible dark matter scaffolding. Theories like MOND, modified Newtonian dynamics, and TVES, a relativistic version, have tried to rewrite this story. They've struggled to explain everything at once, but they haven't been entirely ruled out either. Another breeze carries a more radical scent: extra dimensions. Maybe our universe is a brain, a three-dimensional membrane floating in a higher dimensional space. What we think of as gravity could be leaking into or from these extra dimensions, changing its strength over time. In some versions, these extra-dimensional effects could compress the early universe, making galaxies form more quickly, or change the nature of time itself. You drift closer to a deeper notion. Maybe it's not space that's expanding into time. Maybe time itself is an emergent property, a statistical phenomenon born from entanglement, like temperature emerging from molecular motion. If that's true, then the early universe isn't a time in the usual sense. It's a phase, a state of order, shifting into complexity, and all our clocks are just local illusions. Some physicists have even flirted with the idea that the Big Bang wasn't the beginning at all. Maybe it was a bounce the latest in a cosmic cycle, an endless loop of expansion, collapse, and rebirth. In these cyclic universe models, the seeds of early galaxies might have been planted not just milliseconds after the Big Bang, but in a universe before it. What Webb sees then might not be anomalies, but echoes. It's dizzying, isn't it? You peer at the galaxies again, but this time with a new metaphor in your mind. What if the universe is less like a machine with clear gears and rules, and more like an ecosystem growing, evolving, adapting, full of self-organization and emergent behavior? In biology, complexity often arises from simple rules repeated over time. But sometimes it leaps a mutation, a burst, a rapid flowering. Perhaps the cosmos has its own evolutionary surprises. This idea of cosmic self-organization isn't pure fiction. There are hints like the observed filamentary structure of the cosmic web, where galaxies line up along immense strands like dew on a spider's silk. No one tells them to do this. It just happens out of gravity and chaos and dark matter and time. But maybe there are deeper rules at play, feedback loops. We don't yet understand, symmetries we haven't yet noticed. Still, all this theorizing doesn't change what Webb has seen. The data is there and it's beautiful. It reminds you that the universe doesn't owe us consistency. It offers only honesty. And sometimes that honesty is confusing. It says, here is something that doesn't fit. Do better. And we try, we argue, we rewrite, we observe again, we revise the equations, not because we love being wrong, but because being wrong is how we know we're alive, curious, and inching forward. Cosmology isn't just a science, it's a narrative discipline. We're trying to tell the story of everything starting from almost nothing with only the faintest clues and a lot of imagination. So you turn back to the galaxies. They haven't moved. They're still glowing from 13 billion years ago, still breaking the rules you thought were settled. And in that glow you sense something deeper, a kind of cosmic laughter. Not mocking, but amused, kind. As if the universe knew you'd get here eventually and has been waiting patiently, silently with its next riddle ready. You find yourself now not in the presence of galaxies, but in their shadows, the quiet in-between places of thought, where doubt stretches long and softly like the tail of a comet. By this point, you've seen the impossible, well-formed galaxies that shouldn't be there, quiet giants blazing too early, physics fraying at its edges. And yet, the universe hasn't crumbled under scrutiny. It just smiles and holds its secrets a little tighter. It brings you to a place scientists rarely speak of aloud, the fragile middle ground between confidence and confusion. Not the failure of science, but the exhilarating place where it starts to molt and evolve. The edges of what we know aren't neat. They're foggy, echoing with more questions than answers. You float now in that fog. Let's say, just for a moment, that everything we thought we understood about galaxy formation is true. But these observations are also real. Then we are missing something fundamental. Not a tweak or a patch, but a conceptual shift. Like discovering that Earth isn't the center of the solar system, or that time isn't constant. We're due for another such turning. And the Webb telescope, with its pristine mirror polished in starlight and folded origami-like in space, might just be the messenger. You can almost hear it whisper, "Look again." There's a philosophical thread winding through all of this. A question older than science itself. What is the universe trying to be? Are these galaxies simply natural outcomes of physics playing out over time? Or are they expressions of something deeper, an underlying principle that favors order, structure, beauty, even consciousness? If galaxies form too early, maybe it's because they can. Maybe the universe isn't bound to crawl when it's capable of running. But there's something else whispering in your mind now, soft and persistent. What if? What if the problem isn't out there but in here in us? The way we think linearly, chronologically comfortably nested in cause and effect, might not be enough. The universe doesn't think in human. It thinks in entropy and emergence, in fields and fluctuations in geometries we haven't dreamt yet. Perhaps what we call early and late are meaningless labels, cosmic misreadings, from a brain too accustomed to ticking clocks and kitchen timers. You drift back to the notion of time, that slippery metric we cling to. Time, as we understand it, began with the Big Bang. But that's a local truth. In physics, time is just one coordinate in a relativistic manifold. It's elastic, directional, not fundamental. Maybe there is no before and after, only relationships between states like chords in a melody rather than notes in a line. That would mean these early galaxies aren't early at all. They are simply placed where they belong in a larger structure that we haven't yet deciphered, a pattern too vast for our temporal eyes. And now a quiet theory ripples across your thoughts' conformal cyclic cosmology. Roger Penrose's strange vision of a universe made of successive eons, where the end of one cosmos becomes the beginning of the next, not by explosion, but by stretching time so far that mass and scale become irrelevant. At that edge, time and distance dissolve, black holes vanish, entropy resets, and then a new beginning. In this model, maybe the massive galaxies of today leave behind subtle imprint seeds for the galaxies of the next eon. What Webb is seeing could be their distant descendants looping back from the far side of forever. But of course, that's a fringe theory, elegant but speculative. Still, you can't help but admire it. It has the scent of poetry. And if we've learned anything from the universe, it's that poetry often survives where logic fails. Now you float alongside a distant galaxy again, one of those that shouldn't exist. You peer into its core, and it looks back unbothered. The light it emits has crossed epochs, traversed expanding space, bent around invisible masses, and finally fallen into the aperture of a telescope humanity launched with trembling hands. It is not surprised to be seen. You are the one who is astonished. This is not just astronomy, it is correspondence. The universe speaking to itself through you, through data, through dreams. But back on Earth, the headlines rage. Webb breaks the universe. Galaxies found before time. Physics in crisis. These are not untrue, but they are simplistic. The universe isn't broken. It is merely bigger than expected, more generous, more layered. The rules haven't failed, they're just incomplete, like a map that only charts the valleys and misses the peaks. Somewhere in all of this is the quiet realization that the universe is under no obligation to match our expectations. Our models are not blueprints. They are paintings, impressions, fingerprints of what we think is going on beneath the light. And the moment we start mistaking them for truth, the cosmos gently intervenes with an anomalous galaxy, a misbehaving quasar, a silence where we expected a roar. This is how science moves, not through certainty, but through interruption. Webb is not breaking physics. It is revealing where the edges are, and edges are where all the interesting things happen. You close your eyes for a moment. Let yourself drift. Let the questions expand. Not every unknown is a problem. Some are invitations. Some are the universe's way of saying there is more. And isn't that the most comforting thing of all? You've come a long way through this quiet storm of stars and paradoxes. And now, as the final light of this journey stretches before you, you find yourself hovering between wonder and surrender. You've seen the infant universe through the eyes of James Webb, stared into galaxies that shouldn't exist, listened to scientists question their sacred models, and tasted the edges of time itself. And through it all, one truth has remained constant. The universe is vast, mysterious, and utterly unbothered by what we think it should be. The story doesn't end with those ancient galaxies. In fact, it barely begins there, because every discovery Webb makes now becomes a cornerstone for the next generation of questions. Each too early galaxy is not a failure of theory, but an opportunity an open door at the edge of thought. And this is how cosmology survives, not by having all the answers, but by constantly learning how to ask better questions. More data will come. Webb will peer deeper into longer wavelengths and stranger corners of space. Other telescopes will follow. Ground-based instruments, gravitational wave detectors, maybe even neutrino observatories peeking into the abyss of cosmic silence. And in time, we'll stitch together a clearer picture, or at least a richer tapestry of ignorance. You glide slowly now toward a familiar cluster of galaxies, ones we thought we understood. They seem calmer, more obedient to theory, but even here the shadows are shifting. Some of these galaxies harbor supermassive black holes that shouldn't exist either. Some have stars with elemental ratios that hint at forgotten fireworks, ancient collisions, stellar alchemy from the deep past. The more we look, the stranger it all becomes. And here's a thought that lands gently in your chest, like dust on a windowsill. What if we've always misunderstood what it means for something to not belong? Maybe these early galaxies are exactly where they should be, and it's our framework that's misaligned. Maybe the rules were never rules to begin with, just provisional agreements useful until something better comes along. Think about the Copernican revolution. Once Earth was the center of everything unmoving and supreme, then not so much. We've been dethroned again and again from the solar system, from the galaxy, from the universe's narrative. And every time the cosmos has grown more vast, more impersonal, and somehow more beautiful. This is just the next dethroning. We thought we knew when galaxies should appear. We thought the timeline was fixed. Webb gently says, think again. So now you're floating through this old new universe, not as an observer looking in, but as a participant woven into its very fabric. The particles that make up your body were forged in stars. The thoughts you're having are fluctuations in fields shaped by cosmic inflation. Your breath is a remnant of processes that began before any galaxy existed. You are not apart from the universe, you are of it. You are a question it asks itself. And in that spirit, maybe the early galaxies aren't anomalies. Maybe they are messages. Not in the mystical sense, no one's writing you a letter, but in the scientific one. A signal, a discrepancy, a deviation from prediction that demands attention. That's how all major shifts in science begin, a wobble, a flicker, a wrong answer that won't go away. Imagine a future decades from now, where students learn that yes, galaxies once thought to be too early were the key to rethinking how cosmic structure forms. Maybe it turned out that dark matter doesn't behave the way we thought. Or time's geometry is more flexible than Einstein realized. Or inflation seeded matter in uneven, chaotic ways we hadn't modeled yet. Or maybe we found new physics entirely. New forces, new particles, new paradigms. The galaxies are silent on this, of course. They are what they are. Our job is to listen more carefully. And as the listening continues, so does the dreaming. You imagine telescopes yet to be built, ones that will peer into the cosmic dark, with resolution sharp enough to see stars forming inside these impossibly early galaxies. Maybe we'll map the movements of gas around their black holes, or catch the flicker of the first supernova. Maybe in a few centuries we'll even send probes beyond the solar system, riding beams of light to see the shadows of these ancient structures from new vantage points. And even then, we won't be done. Because this is the true shape of cosmology, not a static knowledge, but a dynamic unfolding. A lifelong, species-long process of reaching, wondering, and rewriting the story as new stardust falls into our grasp. So if you're still lying there, eyes open or already closed, you can take comfort in this strange truth: the universe is unfinished, and so are we. There's still room to be surprised. Now let yourself drift even more slowly. Let go of theories of paradoxes of too early galaxies and questioning minds. You are floating once again, untethered your body, forgotten your thoughts like feathers in the dark. Out here the galaxies begin to fade, not vanish, just recede like candles slowly being snuffed at the end of a long, quiet ritual. The colors dim. The stars soften. Time no longer matters. There is no ticking, no urgency, only the long, soft hush of the cosmos breathing without end. Your awareness curls inward, as if wrapping itself in a blanket of silence. You are not thinking anymore. You are sensing. You are settling. The rush of knowledge, the thrill of the unknown, all of it, now dissolves into a steady warmth. The universe still holds its mysteries, but you don't need to solve them tonight. You just need to float. Outside, galaxies turn silently, light years away their spirals, as slow as sighs. Inside, you slow too. Your heartbeat is the rhythm of gravity. Your breath is the pulse of space. Nothing is expected of you here. You are simply part of it all. Even the questions go quiet. And in that quiet, you feel something rare peace, not from certainty, but from wonder. You do not have to know. You only have to be. Good night, traveler of light.